Hello everyone, this is Ala from Egypt, so please excuse my English. Today we will talk about a great feature provided by Proteus design suite. The feature we are talking about today is analog analysis feature, which is a real-time simulation of your circuit. Let's take an example. The circuit we see here is a simple motor speed controller, depending on pulse width modulation generated by the single chip dual operational amplifier LM358. The first operational amplifier works as an RC oscillator with a Schmitt trigger output. The discharging waveform of this capacitor will be delivered to a comparator, or the second half of the operational amplifier, which will compare the value of the voltage here to the value of this potentiometer. The reason we added R5 and R6 is to prevent 0% and 100% duty cycles. That will depend on your application. If your application requires or allows 0% or 100% duty cycles, so don't use them. Now, to simulate this circuit, we will use a normal oscilloscope to run the simulation. We will take this waveform and this one. If you pressed run here, you will find the expected waveforms. Charging, discharging waveform generated from this half, and the pulse width generated from this half. Those pulses will vary its width depending on the value of this potentiometer. Increasing the value of the potentiometer will increase the width of each pulse, just like we see. So that's the main idea of the circuit, and that's how simulation works. You'll see the waveforms here. According to a frequency limitation of this software, if we increased the frequency by decreasing the value of this capacitor to 1 microfarad, we will almost run on 16 kilohertz. If you run the simulation, it should be the same as the last case, except with more frequency, a higher frequency, higher operating frequency. But you will have a warning message here that the simulation is not running in real time due to excessive CPU load. So this is a software simulation, not a real-time simulation. The higher frequency we use, the lower performance simulation we will have. For example, let's use 0.22 microfarad, which means 72 kilohertz almost. Now we will see the response of the software itself will be slower, and just like you see, the motor didn't get the full speed yet. The time frame here is not accurate. You'll see the fraction of a second will take almost a second. This means that our simulation is not very accurate. The more frequency we use, the lower performance we get. As you see here, everything is running almost wrong. If you change the value of the potentiometer, you might lose the control of your simulation. As you see, changing the value of this capacitor, of this resistance here, would result in nothing almost here. It will take a very long time to take an effect. So how we solve this? We go for analog analysis. What's analog analysis? Depending on those probes you use and the points you want to see the waveforms at or to simulate. Those probes are simply a measurement instruments. You can use them to measure voltage and current. but it's not the main reason we are making this video. let's just rename them to first stage and second stage. If we run a simple simulation or a normal simulation, you will find varying voltage here and here, but the same warning message. So we will go to this icon, which is called graph mode, which will simply draw a screen or a graph on our software. This graph has some properties needs to be set first. The start time of your simulation and the stop time, which means the interval you will use the real-time simulation through. We'll start from 500 milliseconds to 502 milliseconds. We will just run our real-time simulation in 2 milliseconds. That's the first thing we need to set. The second thing is what trace we want to draw or to plot here. Let's take the first stage probe or the first stage trace. Right click here will give me an option of simulate graph. If you look down here, you will find a counter, a percentage counter, which means that ProSpice is running a real-time simulation. So the waveform we will see here is the real waveform we will see in real life. That's it. Simple as that. What will happen if we add one more trace? I'm sorry for that. We should see the effect of changing this potentiometer on the output waveforms. The output waveform from this operational amplifier will be delivered and applied to the gate of this MOSFET IRF 3205. This one will control the speed of this DC motor depending on the width of the pulse we have here. As you see, since we have a low value of RV1, we will have a narrow pulses. Increasing the value of RV1 will increase the width of the pulses, which means a higher DC motor speed. So that's it. This is the final waveform we get on a frequency about 732 kilohertz, which you will never ever get this value with the normal oscilloscope in the software. Now we need to add one more trace, but we will measure the motor current. A click on this probe and dragging the name to the graph will add the trace automatically. Now we should see 3 plots. One green plot of the charging and discharging curve of capacitor, a red plot of the output applied to the MOSFET gate, and a blue plot that's motor current. That's what you see. So, to make it more clear than this, we will delete this graph and add a new one, just to see the waveform of currents through the motor. Using this feature will make you able to simulate any circuit with any operating frequency, depending on the time interval you select. If you choose a long time interval of simulation, it will take more time to simulate, and you might face a zero output, no output at all. So this is the output waveform of DC motor current. Using the feature of analog analysis will give you the ability to simulate each and every part of your circuit, no matter what operating frequency you are using. This will solve a lot of problems concerning switching circuits, such as DC to DC converters or switching mode power supplies, and will give you the ability to monitor the voltage and current through the entire circuit in a real-time simulation, which will not be possible using a normal oscilloscope. That's all for today. I hope to meet you soon, and goodbye.